everyone. Welcome back to Learning at 11th Hour. So, today let's just discuss a few more problems related to mesh and nodal analysis. And this particular problem was asked in GATE in the year 2021. It was a doubly paper. So, let's see how we can approach this problem. Here, we have been asked to compute the value of beta such that Vy should be equal to 0. So they are saying if Vy is to be 0, then what should the value of beta be? Now, looking at this circuit, we see that we could apply the super mesh analysis here too, because see, there is a current source over here between these two uh, meshes. But we have to consider that we need to assume that this Vy is equal to 0, and Vy is nothing but a nodal voltage. So it would be better to approach this problem using the nodal analysis. So let's approach this problem using node analysis. Here, this being node N1, this is node N2, this is node N3. I'll consider this to be node N4 and this one is node N5, both of which are super nodes in the sense that the nodal voltage value V4 is going to be 6 volts, and the voltage value at this particular node N5 is going to be beta into Vx. So we are not going to be very concerned about these two nodes. We are going to frame KCL equations for node N1 and N2. So applying KCL at N1, what do we get? So let's consider that there are three currents that are leaving out of node N1 in this manner. So to write the equation for this particular current over here, we get minus of, because it's leaving the node N1, minus of Vx minus 6 by 1. And for this particular current through 4 ohms resistor, minus Vx by 4. And for the current through 2 ohms resistor, we can write it in terms of the nodal voltage Vx as minus of Vx minus Vy by 2. All this put together is equal to 0. So let me simplify this. So we can now take 4 as my LCM. So we'll get minus 4Vx plus 24 minus Vx minus 2Vx plus 2Vy is equal to 0. So this turns out to be uh, minus 7Vx plus 2Vy is equal to minus 24. Now the question says that we need to compute the value of beta such that Vy is equal to 0. So if I consider Vy to be 0, then what is Vx? So Vx turns out to be 24 by 7. So let's consider this to be my first equation. Now, if I am going to apply KCL at node N2. So here again, let's consider these are the currents that are leaving. 2 amps is from a current source, so I'm not going to disturb the direction. So that is entering Vy. So I'm going to say plus 2 minus of Vy minus Vx by 2 minus of Vy minus beta Vx by 3. All this put together is equal to 0. So these are the three currents associated with node N2. So now again, we can simplify this. We can take 6 as our LCM, and what we will get is minus 3Vy plus 3Vx minus 2Vy plus 2 beta Vx is equal to minus 2. So when we cross multiply, this would become minus 12. Let me consider that the Vi's are 0 over here. So what I will get is Vx 3 plus 2 beta is equal to minus 12. Now, in place of Vx, if I replace 24 by 7, so what would I get? So let me replace Vx with 24 by 7 and keep the remaining. So here I have 2 by 7. So that would turn out to be minus 7 by 2 is equal to 3 plus 2 beta. So further simplifying, we get minus 7 by 2 minus 3 is equal to 2 beta. So what is this? This becomes minus 7 minus 6 by 2, which is minus 13 by 2. Now 2 beta is minus 13 by 2. Therefore, beta will be minus 13 by 4. So if I rewrite this, beta is equal to minus 13 by 4, which is nothing but minus 3.2. So they've asked us to round it off to two decimal places. So the answer should be minus 3.20. So that should be the value of beta, so that Vy over here is equal to 0. So this was the gate problem asked in the year 21 in the EE paper. Let's move on to the next problem. Now this is another problem which involves the concept of supernode. So they have asked us to compute the values of V1 and V2. So as we can see, V1 and V2 are two non-reference nodes between which there is a voltage source connected. So we can consider that this node, these two nodes put together, these two non-reference nodes put together can form a supernode. Now let's analyze the node where we have marked V1. See, if we look at this node, there is another one over here between which there are no elements connected. So which means that this particular node N1, and let me call this as N1 dash, both of these nodes are actually one and the same because there are no elements in between. So this is also precisely node N1 too. So when I consider the super node, this entire thing is going to act as my super node for this problem. So now let us apply KVL at the super node. So when we do that, we need to mark the voltage drops, and for that we need to know what are the direction of currents. So let's consider that in the half ohm resistor the current is like this. I'll call it as I1. In the 1 by 6 it is say I2, and the other currents are 4 amps entering this node, 9 amps entering this node, and I'm not considering any current over here through the 1 by 3 ohm because it falls under the super node, and in any case it would get cancelled out. So let's begin. Here the drop is going to be in this direction. For this it is going to be in this direction. For this it is going to be in this direction. So we have, considering this clockwise to be my direction, I have 5 volts plus 1 by 6 into I2 minus 1 by 2 into I1 is equal to 0. Now, let us apply KCL at the supernode. So, when we apply KCL, this entire thing, these three dots, that is N1 dash, N1 and N2, all of these are actually one particular single super node. It's just one node. So there's just going to be one equation, and we are going to consider all the currents that are entering and leaving the super node here. So we have 4 amps which is entering, so plus 4, and we have I1 which is leaving, so minus I1. We have I2 also leaving, so minus I2, and 9 amps entering, so plus 9. All this put together is going to be equal to 0. If I would have considered some current, let me call it as I3, right? So say I consider I3 is entering the node N1, then it would also be leaving the node uh, N2, right? So then there would be a plus I3 and a minus I3, which would effectively get cancelled out. So I'm not considering any current as such from this particular direction. Now, this is my second equation. I can actually simplify this equation in terms of my nodal voltages, where I have plus 4 and I1 is nothing but V1 by half. So there is a minus sign here. minus V2 by 1 by 6 plus 9 is equal to 0. So now I have uh, minus V1 by half minus V2 by 1 by 6 is equal to minus 13. So simply putting this, we can get this as 2V1 plus 6V2 is equal to 13. Now, if we look at equation 1 closely, we see that 1/6 of I2 is nothing but V2 and half of I1 is nothing but V1. So, this can be replaced with V2, the node voltage V2, and this can be replaced with the node voltage V1 because after all, the drop across the 1/6 ohm is V2 minus 0 volts, and the drop across half ohm is V1 minus 0 ohms. So I can get my other equation with the two unknowns as minus of V1 plus V2 is equal to minus 5. So now if I call this as equation 3 and this as equation 4, now these are the two simultaneous equations which I need to solve in order to get the values of V1 and V2. So here we would obtain V2 as 0.375 volts, or which is nothing but 375 millivolts, and we will get V1 as 5.375 volts. So you can solve these two simultaneous equations manually also, and you can also use the calculator to do it. So that's all with today's video. I hope the concepts that were applied in solving the two problems are clear to you. If you have any queries, please do not hesitate to post them in the comments. Thanks for watching. Please do subscribe to my channel for more such videos on circuit theory. Bye bye.